is your trainer Arul Francis, and I want to quickly introduce to you about my background before we get on to the session. I have about 10 years of experience in the field of analytics and artificial intelligence. I started my career in 2007. I started working with an investment bank, Lehman Brothers. I was part of the global risk team, and part of my job was to actually help estimate the risk most of the accounts were exposed to and move to I2 decisions in Chennai. And that's where my current role is. As I2 Decisions, I'm leading the offshore delivery center completely in terms of delivery of projects and also in terms of the ability to come up with solutions for our clients. Our Center of Excellence team is working on AI projects. We are doing a lot of projects from chatbot to text summarization to image classification, all of that using deep learning and TensorFlow. So we are at a very, very exciting stage at this point in time where we are using tools like TensorFlow, Keanu, and Keras, and techniques like deep learning techniques like CNN, RNNs, LSTMs, and sequence to sequence models, which are very, very important in terms of being able to actually create some very solid use cases, which are very, very helpful, especially in terms of businesses and their ability to solve a lot of problems. So that is what we are going to talk about, a very small part of it, which is probably deep learning. In fact, our sessions or our courses that we do in Edureka have a focus on understanding and going through all of these concepts in the depth and try and understand how this can be implemented across use case. And one of that is what we are going to discuss today, which is basically understanding what artificial intelligence is in the applications of artificial intelligence. Most of you must have read about it, but I want to call out some very specific use cases. Then within the subset of artificial intelligence, there is this one important part which we call as machine learning. And we want to clearly outline what are the differences between machine learning and deep learning. And deep learning comes through something called as neural network, and we will also look at a hands-on use case of neural network, right? At this point in time, I see a couple of hands raised. I just want to check if there are any specific questions. Let me see who's that. So Simran, any questions at this point in time? I see Simran has raised their hand, and I'm guessing at this point, any questions, right? Simran, please feel free to use the questions panel as well if you have a question at any point in time. Just to let the audience know, if you can please put your questions, I will take them up immediately. But in case, I'm not able to take the question, I promise you I will definitely get back to the question before the end of the session. But at any point in time, if there is something you need a question, you need a clarification on, please put that in the questions panel. I'll try and get back to you immediately, but in case I don't, definitely I will get back after having discussed a specific point, and then I will probably take up the questions. So Samarth, good question, which is recording be available after this session. I do have the moderator here. I think the team from Edureka is also available. I'll definitely ask them to get in touch with you, Samarth, and probably see how we can work that out in terms of the recordings or any other information that you'd like to get in terms of the current session that we're doing. All right. I hope that answers your question there, Samarth. All right. So in brief, we've just discussed about the agenda for today. But let me actually start off by talking a little more in detail about artificial intelligence. In fact, that is the reason why we are in this session today, especially at a time when the IPL match is happening. We're actually listening to a session on artificial intelligence because the reason is that we are at the cusp of technology, I would say, or we are at the beginning of a new revolution, if I might call it. And this is actually the right time because we have all the computation power we need, we have all the techniques that we want, and we have all the data that we need. That is why, artificial intelligence has become this new word that is constantly used for almost every other industry. Remember, the objective is to try and automate a lot of the regular work, and you don't want to explicitly call out all of these events and automate them, but rather you would like an intelligent mechanism by which all of these happen. A lot of people generally tend to ask this question during the start of the session is, hey, why is artificial intelligence all of a sudden such a big thing? People who come from machine learning background usually ask the question that, hey, aren't we doing machine learning? Weren't we doing this for the last 5, 10 years? And how is that now artificial intelligence takes a lot of, important role and has got the ability to actually get so much amount of limelight in the present scenario? So the reason why that happened is initially we didn't have the amount of data. So data wasn't being collected to the limit or the extent to which we wanted it for doing some of our analysis or to do some of the automations. Now with the ability to scale all of your data using cloud, you can store as much data as you'd like to. So it could be in tons It could be in GBs, it could be in terabytes and multi-terabytes that you could think of. The other part of it is the processing power about it, right? So all this data is available now. Now you need something to process it, and again, cloud is giving you the solution in terms of being able to use all of the computational power available within some of the vendors like AWS or probably Azure. They're giving you so much power that you can actually do all of these computations. The remaining part is the application of the technique itself, and that is where I think data scientists like us are actually the need of the hour, where we need people who can actually analyze all of this data and use all of the computational power. And that is where our focus on the session is also to be able to help students or to be able to help our participants in terms of the ability to understand the different aspects of deep learning and how they can exploit all the functionalities available within tools and technologies outside to be able to create some really cool automation. And as mentioned, artificial intelligence is the ability to, intelligently understand data and then be able to take action against any provided data. So that's what we're trying to do, something that is intelligent, generalized, and does not become too particular or focused on a specific use case. Dependency on artificial intelligence. So we're just going to briefly pull out some very important use cases there. Artificial intelligence has a lot of dependency, and one is AI for Good, where the team at Stanford is actually analyzing satellite images to be able to identify specific areas or specific regions where there is a lot of poverty or areas which are actually being denied some of the basic human necessities. So what we are doing is we are using AI not for just profits and whole lot of enterprise level projects, but rather for very important things like trying to find out through satellite images if there is existence of poverty and how we can overcome some of those things. Aviation is something that's been using AI for a long time. From the mechanical part of it, they've been using it to analyze engines and predict failures, and also at the same time try and create efficiency for airlines and be able to, create a bottom line growth for most of the airlines. So that is one aspect of it, and then there is the business aspect of it, where there is the ticket price determination, which is a dynamic pricing model trying to predict what is the right price the user will pay and make sure that you provide the right price so that you have a conversion in terms of aviation aspect of it. Education is something where the important thing about application of AI comes in there, because there are a lot of projects where people are trying to actually understand the different characteristics of students and then be able to actually customize some of the content that is there for these students. Now, there are a lot of things that are happening in terms of education. In fact, there are very successful projects that have been implemented, and Google is also coming up with its own tool that is more focused on education for all, which is basically trying to make sure that there is a very customized learning and teaching methodology that can be implemented for students to enrich their knowledge through a personalized interaction with the systems. In terms of healthcare, I think I don't even need to talk in length about it. I just say one word, which is probably everybody's heard of, which is basically IBM Watson, and that's an artificial intelligence framework that has been able to garner so much amount of respect and so much amount of efficiency in terms of its ability to work on healthcare related projects. And very simple thing. In fact, this is a very interesting use case. I encourage all of the participants to actually go through is to go and read about how IBM Watson is actually implemented at in New York for Sloan Kettering, which is actually a cancer research specialty and a hospital that's focused on curing cancer. So you can actually see IBM Watson has been able to help a lot of oncologists in terms of trying to find out, first from the diagnosis perspective, being able to read through scans and reports and be able to predict the chance or probability of a person having cancer. And the next thing is, once it detects cancer, it can also, on the basis of your data, help and identify what is the best path or best treatment plan that should be there. Remember, cancer is very, very specific. So the treatment plan that is for a particular person changes from people to people. And you need to have an algorithm that can identify people and with less amount of error, be able to help out people in identifying the best possible, cure or best possible plan in terms of the treatment to help them recover fast and be able to do well in life as well. So that's where healthcare is, and I'm not going to go much into it because I know a lot of people must have read about it. And if you've not, I would encourage you to read about it. You'll really find it interesting. And some of these are path-breaking technologies because remember, these are impactful projects that are actually changing the whole mankind at this point in time. And that's what we all aim for in life, right? To be a part of a project that actually changes the very perception of how society looks at a particular technology or tool. In terms of heavy industries, there's oftentimes the most important thing has been talked about is automation and how we are removing some of these things. And very interesting use cases about the offshore drilling centers where a lot of metrics are captured in terms of extraction and failures of machines. And that's where you have very smart and intelligent AI tools that are available that can actually detect failures. And the other things are in terms of repetitive projects that are done, which can be actually automated through a learning process through data. You can have a model actually understand and predict exactly what kind of action needs to be done. So from heavy industry, again, there's a lot of use case. And then from the finance aspect of it, I think the trading part of it is one where, time immemorial AI has been a very important concept. In terms of it, it's also in term, algorithmic trading and risk and a whole lot of things that actually come into it is where artificial intelligence has been doing a lot of job. In terms of finance, I think there are enough and number of use cases that are there outside. And as far as we know, I think TensorFlow is something that's widely accepted in the area of finance itself, considering because TensorFlow has the ability to process such high data or high frequency or high intensity data, if I might use the word. And that is where the important thing about TensorFlow and also deep learning comes in. I'm going to take a quick pause here, and before I proceed to the next slide, I actually want to quickly check with the participants. I see that a lot of people are very quiet. If there are any questions that people have at this point in time, I would like to take them up and then proceed to the next slide before moving on to the next slide itself. Any questions at this time, guys? All right, no questions. I'm hoping the students are finding it interesting. The participants are finding it interesting. All right. Or I'm guessing all of us are waiting for that one moment where we can actually see AI in action. So I'll do that. A question here from Rohit, which is when do you decide a business case needs AI? I think the most important thing is to look at how much data is available, Rohit. So I'm going to put in a important term and condition, if you might call that particular part of it, which is that the implementation of AI depends a lot on the type of data that you have. So if you want to completely automate an entire process, it completely depends on the amount of data that you're already capturing. But considering now we are in the world of open data, a lot of data is available on the web and a lot of data is also available on other sources. Data does not seem to be the issues, but rather you look at the ROI of implementing an ROI, implementing an AI, sorry, and you have to look at how much cost is going to be involved in developing an AI solution by replacing, let's say, a process being driven manually. If the manual process outweighs the AI solution, then that indicates a reason for moving to AI-based methods. Also, remember one more thing is that AI does involve cost running on cloud, and also in terms of the amount of data that you're going to store, all of it takes a certain amount of cost. So both of these factors needs to be taken in, Rohit, before coming to a conclusion on which business needs AI, basically. Okay, Abhimanyu has a very good question. In fact, Abhimanyu, I'm actually in the midst of this problem, so I think I'll take up this question and I will actually answer this, in a little detail as well. So one of the things that Abhimanyu asked here is he would like to know how a web application developer will use AI and ML and to what extent he needs to understand it. The very common problem that we are facing, in fact, is websites have become rather static, and in fact, the world of apps have taken over a lot of the website business right now. Now, one thing is the reason why we prefer apps over, websites is because of the fact that they are available in mobile and they're also available in terms of at any point in time. The other thing is we consider websites are very important is because you know websites have the ability to serve content dynamically, which means you have the ability to personalize the experience every user has. This was not the use case 5 or 10 years back. Now you've got the data, you've got the kind of users who are coming into your website, you have a pretty good idea of who they are, and now what you want to do is personalize your website towards their experience. And the entire web experience changes when you're actually creating a personalization element for them. And that is where AI is actually coming in. So your ability to analyze different features or different aspects of a particular user and then be able to serve content dynamically is one use case. Could involve recommendations, could involve a certain element of changing the interface for them, or probably being even more personalized, which means if you notice a user is coming quite often, how can you actually communicate with them? And in fact, the important thing is nowadays most of the websites have started to bring in chatbots. So what they want to do is they want to not only leave the website as a static thing that resides on your Chrome browser, but rather be a communication tool between the backend organization and probably the front end in terms of the user. So a lot of use cases trying to stream data, understand what are the different types of customers and personalizations, recommendations, and then the final aspect of it is to bring the chatbots, which are trying to bring in the human element of interface of discussion with the particular customer as well. I hope that answers your question, Rohit and Abhimanyu. How AI will help in analyzing the video analysis. So a lot of use cases, Prasanna, there. Some interesting use cases are, captioning a particular video, classifying different streams of videos as well. And usually these kind of techniques use techniques like RNN or LSTMs that we talk about. So a lot of applications in terms of captioning, and as I mentioned, the classification of frames and then be able to correlate different videos is something where AI is being actually used. Rohit, Abhimanyu, and Prasanna, I hope I was able to answer your question. Would appreciate a quick yes or a no. In case no, then I can probably look at what else I can provide as an answer to you guys. Thanks, Prasanna. I hope Abhimanyu and Rohit, the questions were clarified. All right. As we move on, let's look at artificial intelligence. Now, remember, artificial intelligence is a macro concept, and there are micro aspects to it, like machine learning. And within machine learning, there's another super micro concept called deep learning. Now, when you stretch the globe out and when you flex it up a little bit, artificial intelligence is not something that started up somewhere in the last 5 years or 10 years, and then suddenly, we have a situation where artificial intelligence becomes this new thing. No, it's not that way. In fact, earlier artificial intelligence was available. In fact, a lot of us were applying it. But the only thing with artificial intelligence in those cases was that all the outcomes had to be hard coded. Now, let's assume a simple example, right? I mean, in case you wanted to actually install a heater in your house and you want to connect it to, let's say, a software, and you want that heater to behave dynamically in the sense based on certain situations about the environment, it has to be able to heat or cool the water basically, right? Now, if I'm just giving that for an arbitrary example, but in the situation like this, what is confusing is because there could be multiple outcomes. I might have multiple scenarios under which I would like to have water. So I could probably want hot water on winter days, which could be a very macro concept, and I could now want cold water on, let's say, summer days. And the second thing is, on days when I go out for a workout and I come back, it should be able to provide this degree of water. When I go to office and come back, it should be able to provide this amount of water, or this heat level is what it needs to provide. But the problem with that is there could be multiple preferences that I might have, and to be able to call out these preferences programmatically, or rather hard code them in a particular program, is going to be a very difficult thing. So earlier, people solved the process of automation through some hard coding, but they quickly realized that this is not the optimal solution, because there's a high possibility that you might end up calling out too many outcomes, and to be able to hard code all the outcomes is humanly impossible. So we needed a technique which can intelligently learn some of these things, and all you need to provide is a list of all the outcomes, and intelligently the data which is provided as an input is read by the algorithm and is able to apply it for different use cases. And that is where machine learning actually comes in. And not that machine learning didn't exist. In fact, the concept of machine learning has been there probably 200, 300 years back. If you talk about even techniques like linear regression or logistic regression, these techniques have now got the computational ability. As I said, the algorithms were all there, the computations were all there. All we needed was the calculator to do this. And that's where now we have all of these tools in our hands. So the tools of the war are in our hand. All we need is just a war to begin, right? So that is where machine learning has come in, and a choice of the right technique helps us to kind of automate a lot of processes. But remember, uh, we have now in the last few years started seeing that data itself has changed its type. And the major thing is data is no longer in the most structured type of rows and columns or Excel sheets, but data has started to move to the unstructured aspect of it. And when I talk about unstructured aspect, I think all of you can relate, right? I mean, earlier we used to share jokes on text and using some other factors, but now most of us are sharing images and videos and pictures and text in multiple different formats and emoticons and whole lot of things, right? Our communication is dynamically changing, which means we are talking in things that are not necessarily restricted to a particular type. So that is where the importance of actually AI or deep learning comes in, the ability to handle unstructured data. So to me, if you ask me what is the difference between other machine learning techniques and deep learning, is simply put, deep learning takes up unstructured data like it's a piece of cake for it, right? So it's just breakfast for deep learning when it talks about unstructured data, and it is very, very powerful. It is very intuitive to actually implement deep learning, and the simplicity and prototyping of a deep learning is easy, so it is possible to work on any type of data. And as mentioned, some people had asked, how do we apply video? How do we do it on images? Any use case, you don't need to worry about it. You have techniques that can actually take care of all of them. So a follow-up question from Abhinanyu actually, and I'll take that up here. As a web developer, will I mostly be using existing libraries and incorporate them in my application, or you need to understand ML and AI in great depth to be able to use them optimally? So to your question, Abhimanyu, to a certain extent, you will not be using your existing libraries because those libraries are more specific towards the application development aspect of it. The libraries more specific to ML and AI are on the data aspect of it, which is to be able to analyze the data and then be able to look at different computations to be able to optimally decide what needs to be done. Maybe there could be a couple of overlapping libraries that could exist, but on a whole, most of the libraries that are specific to ML and AI are different. In fact, TensorFlow is a very different library, although it can be applied in multiple environments like JS, or it could be possible to implement in C++ or even Python, although our session today is going to talk about Python. But what you need to understand is a very good thing that you already are aware about is the kind of data that actually comes from some of the websites. But what you need to focus on is to be able to understand how to optimally use this data. So that is where the focus on the sessions is going to be actually. Another interesting question, in fact, Neetu Kumari has asked this, which is how is AI implemented in cloud computing? So remember, a lot of the models are not actually implemented on CPU. When I'm talking about images, a simple image like, let's say, a simple image that our phone clicks probably is about 1,000 to 1,000 pixels. That's about huge amount of data that actually goes in for an algorithm to actually analyze. When we are talking about text, it seems, for example, a chatbot probably is training on a lot of chat instances that have happened in the past. And typically, a good chatbot is one that can learn on 3.5 million data sets. And so there is a lot of data that is available. And to be able to process all of this data, CPU is definitely not possible. And probably some of the in-house servers can take care of it. So on-premise servers can do that, but then how much can you scale it is where the problem is. So cloud allows you the flexibility to scale depending on the kind of data that you have. So that is where AI is implemented using multiple use cases. You have data storage within cloud. You have the processing aspect of it. Although I'm not a very good cloud expert, I'm not an architect on that, but just a couple of things that Azure or cloud, Google Cloud, or probably AWS offer in terms of different packages that help you to actually process all of this. So that is where it's implemented. in terms of AI. Yes, that's correct, Abhimanyu. We'll be using ML in AI libraries. Absolutely, Abhimanyu. So the question is, Abhimanyu is actually, I think, more than a question. It's a point which is basically, is there a need for an application developer to understand ML algorithms to make applications more intelligent? Absolutely. In fact, an understanding of the ML algorithms is very important because uh, it's a it's a knife for every problem, basically, right? So you don't want to use your tools for every problem. You want to intelligently make a choice on what kind of tool you would like to use to solve what any kind of problem that you actually have, right? I hope I was able to answer the questions, Neetu Kumari and Abhimanyu. I hope I was able to answer the questions. Neetu, I hope you can quickly confirm if the uh, question was answered. So now we've discussed what is machine learning. In fact, I mean, what is artificial intelligence? And we discussed that the subset of artificial intelligence is where machine learning comes in. So let's look at what machine learning is, in fact, right? Um, Most commonly, a lot of you must have come across this. When you actually did your research on machine learning or on AI, you would have come across this problem, which is a very common problem. We call it as the hello world of machine learning, in fact. And what it does is basically you have data on the features of different flowers and species of flowers, rather, right? So the features are basically what you're looking at over here down, which we call as the sepal length, sepal width, petal length, and petal width. Now, every flower or every class of flower has its own unique set of features, and the combination of these features help in determining what species of flower it belongs to. There are typically about 150 different instances, and for a human mind to read through all of these different features and different instances is going to be a big task. So what happened is it's actually a use case from the UCI machine learning laboratory, and what they've done is they've actually built a model based on the data that was available to predict any new species of flower that exists. So all you need to do is you need to provide just the four important features, which is the sepal length, the sepal width, the petal length, and the petal width. And automatically, based on the 150 instances that were provided earlier, the model is able to learn and apply this on the new instance that you've just provided and be able to intelligently classify what species it belongs to. So that is a very basic understanding of how a machine learning algorithm works. And it could be scaled up to different problems. So it could be scaled up to probably if you can identify what species of flower is there, you can also scale that up to look at images and find out if the image is of a dog or if it's of a cat, or probably even what breed of dog it is also to a certain extent. You can do that if you can provide the training for an algorithm. Now, if you talk about images, the complication is that images have multiple pixels, and there's so much amount of dimensionality that exists in the images that we need to actually analyze this very carefully and process all of the elements intelligently to be able to actually classify them. Because remember, any misclassification of calling a dog a cat or a cat a dog is definitely not the most optimized use of an algorithm. So we need to intelligently help an algorithm to make some of these use cases. Now, there are a couple of limitations that machine learning itself comes in with. And as much as I'm a proponent of machine learning, I call out openly the situations at which it might not work. Now, it's easy to make it work when you only have the image of a dog, but let's say that the dog is a part of an image or a family pic, basically, right? Now, this is a high dimensional image. There are a lot of factors that are to be seen in this particular image. There's probably, as you can see in this example, there's the mother, there's the father, there's a kid, and then he has a sister, and then there's the dog. So an ML is actually going through all of these factors before being able to look at this one small piece over here. So the nitty-gritties of the data, or rather, I would say, the ability to look at very small features is where an ML actually starts to fail a little bit. So when I talk about ML, I'm talking about techniques like support vector machines, naive Bayes, techniques like XGBoost and random forest. These techniques can do image classification, but remember the problem is that the abstraction level on images or the high dimensionality that exists on unstructured data is simply very difficult for any of these other machine learning algorithms to work with. So what happens is that they typically start to have very low accuracies. And if I'm talking about this particular case, let me bring it into a real life context, although we are not, our objective is not to classify dogs and cats, but there could be another scenario. Let's say you have a CT scan report or a PET CT scan report, and that report needs to be actually analyzed as an image to find out where there is a particular problem in the particular scan. Across different training examples, you can train out different classes of problems, and it has to look at minute levels of the scan report to be able to find out what exact problem is this. And that is where, if there are these small little aspects or very few pixels that actually cover the problem will be there, is going to be a very tough task for other support vector machines. That is the reason why we actually work out with tools that probably have to overcome the machine learning shortcomings. And to overcome that, the unstructuredness and the high dimensionality of the data is where deep learning comes in. So, uh, every sword has its own unique reason. So here is where I make a very important point, and that is, I'm not saying that machine learning doesn't work or it is not useful at all. There are certain use cases where machine learning is absolutely applicable. Now, for instance, you want to actually predict a credit risk, for example. You want to identify who are the people who are likely to default on a loan or not. Machine learning is absolutely like a knife on a butter. It can work through very well, predict on all use cases without absolutely any misclassifications, or at least you have a lot of control in terms of trying to take care of all the misclassifications that happen. So that is where a lot of machine learning is absolutely applicable and as a huge use case. I'm going to quickly talk about deep learning. In fact, we're going to talk about what is deep learning and its application. But before I get there, I'm going to again quickly take a pause and check with all of the participants if there are any questions, if there are any clarifications, or if even any points that you'd like to make at this point in time before we actually proceed to the next part of it. Does so Rohit has a good question, which is does ML different from IoT? ML could be a part of IoT, Rohit. So in fact, IoT is a larger concept like artificial intelligence, and in IoT, you're talking about connected devices. A lot of these devices could probably require a certain level of artificial intelligence to automate some of the tasks given the data. So ML is probably a component within IoT, is how I would like to put it in this particular case, Rohit. Any other questions? I don't see much questions. I'm hoping that I'm actually clear, unless the student and the participants feel that this is Greek and Latin that I'm talking. But I'm hoping I'm clear. But a quick thumbs up or a quick yes if anybody's finding or anybody's thinking that this is a little different or not able to understand what the trainer is talking about. So feel free to let me know that. That itself is also good feedback, so that I can, try and clarify some of your doubts. Because at the end of this session, what I am looking at objectively is that you have a good understanding of where AI works and what is the technicalities of AI is basically is what I'm looking at. And then probably that triggers in the passion to actually learn in a little more depth about AI as well. So I'm hoping I'm able to actually answer most of the questions or clarifications that the participants have. Feel free to use the questions panel, guys. Do not worry. Be more than happy to answer at any point in time. Now, deep learning actually starts from, or origins of deep learning actually come from a technique called as neural network. And the word neural network itself is how our neurons within our brain actually process all of the information. So if you would like to call it, deep learning is actually a simulation of how our brains think and analyze data. So that is where I'm going to quickly call out very categorically how our brain actually processes information. Um, the general way, absolutely, Prabhakaran has asked about speech recognition. Absolutely, Prabhakaran. I'll answer that question in a moment from now, while I just bring in this similarities between deep learning and our biological neuron. For our brain, right, there are five inputs basically is what I call the five senses is what the inputs are basically for our brain. So I think all of us have the vision, the sense of vision, the sense of smell, taste, touch and feel, perception. All of these are basically senses that are there. These senses are the input data for our brain. So let's take an example, right? So you look at an apple for now, right? An object, for example, is an apple right now. How did you know that it was an apple, basically? So your eyes projected, let's say, a certain degree of light or something on that particular object. And once your eyes actually looked at the object, you perceived all the features related to that object. So for an apple, you looked at possibly the length and breadth of it, probably also tried to estimate what weight it is, and then you basically looked at what color it is. When all these things actually came together, your brain actually quickly took a decision and said that it's an apple. So what happens is in your brain, basically, or in our brain rather, the moment you look at a particular object, there are chemicals that are passed out from our dendrites that we are seeing over here. So they receive all the signals from the senses, they process it and send it to a cell body. Within a cell body is where all of these aggregations are taking place. Remember, you can also touch and feel the apple, you can smell it, and you can probably look at other things. So when all of these five senses aggregate together, they're processing all of this information. So there is a judgment table, if you might call, within your cell body that is taking all of this inputs, and it is putting them together, and then it is saying that it's an apple. And then once it's known that it's an apple within the cell body, it passes it on to another cell to probably take some other action, which means once you know it's an apple, the next action you take is to cut it or probably take a bite of it and quickly finish it off so that you can have a good meal. So how deep learning is working out is it has to take input data. In this sense, probably the input data could not be the five senses, but rather the data could be the ones that we are actually going to provide. Um, so it's very important to understand how our brain works because sometimes in fact, I've started to appreciate a whole lot of things in terms of how our brain is actually able to process information, things that we take it for granted, right? Subconsciously, our brain is doing a million calculations, and we start to appreciate it more when we actually see deep learning in work because you can see how much amount of processing actually goes in to be able to develop a very strong model with great applications. And it is probably one-fourth of what our brain does, but still, it has got so much amount of computation that needs to go. And imagine the amount of computation our brain does. So that is where the interesting concept of, neural networks being a kind of simulation of our brain is an interesting concept. I have a quick question here, in fact. Abhimanyu's question, which is basically, is AI and ML development treated as a career completely different from application development, or it overlaps to some extent with application development? In fact, the entire thing, Abhimanyu, is that although people start to associate, and I certainly feel this is sometimes a wrong association, is that people start to think AI and ML is very much only for data scientists and people who deal with data are supposed to work on this. But in my opinion, I think every person who is working on application development should be a part of AI. The reason why I say that is because, the only missing component mostly in most of the application development is basically bringing in the AI aspect of it. And it's not rocket science that it is very complicated or it is very, very, different. It's all about getting the components together, which is important. And that's what focus on trainings are usually, which is basically trying to bring the components together. Once the components are there, integrating it within your application is just probably another component like putting together, let's say, a component that could probably fetch data from somewhere in the backend. I'm just giving a simple example, although I know I'm dumbing it down really low. But then what I'm trying to say at the end of the day is that bringing these components of AI and ML within your application development only enriches it. And I personally am a proponent of the fact that AI and ML should not be restricted to data scientists. In fact, every person, right from this leadership to all the way until a person who's on to development and right on the floor, building applications to bringing things together should be available or should work on AI because at the end of the day, AI is all about how we train it, and we all are intelligent about our work. We know about our work, and that is where a data scientist is not a specialist in a particular aspect of the business. And that is where people who are in app development know what customers want, know what users look for, and integrating AI and ML there tries to add an advantage to the application that is there. So in my opinion, I don't consider them as two different streams. I would rather say it's a part and parcel of the entire application development. To the question of Prabhakaran, can you explain a bit about speech recognition? So speech itself, looks at multiple data points actually in that particular case. To be very specific, I think it looks at different aspects like pitch and bass and the amount of different the different things that go into a particular part of it. This is stored in unstructured format. It is converted into a structured format before it actually goes into an algorithm. So different parts of speech or different types of speech are uploaded into a model to be able to analyze the different tunes and different pitch and different levels of I'm not sure about the exact terminologies used within speech, but all of these are taken into consideration before being able to classify them and recognize them basically. So just like image, your image is unstructured, but converting it into a structure basically to be able to understand the application of speech recognition. I hope that answers your question, Prabhakaran. Right, thanks for that. So moving on, guys. Now that I have defined how a biological neuron works, it is but obvious that we need to also define how a artificial neural works. So we call it as an artificial neural network or an artificial neuron or a perceptron, whatever the words are. But at the end of the day, it signifies basically, a processing unit, basically, right? So as you see on my left side, you can see X1, X2, and Xn. These are the input data. Consider them as basically your five senses, right? So in this case, for algorithm, it's not necessary that the number of inputs have to be restricted to five, since we are dealing with a lot of data. You can have multiple input factors that could actually help in determining. And the next thing is basically you have a set of weights that are associated with every input data points. What do I mean by weights, basically, right? So there's a certain threshold you have in your mind, right? So you know that a combination of color and also a combination of, let's say, weight, for example, let's say 5 grams or 10 grams is an indication of that it's an apple. Less than 5 grams is basically what we would call as basically, in this case, at least a peach, for example. Now that 5 grams is actually called a threshold, but I'll come to that later. But the learning process of being able to associate a certain level of weight with the input is what the weight over here also does. Subconsciously, we have created weights for every object, which means we know what is the likelihood or what is the importance of certain features in identifying a particular object. So it's possible when you're looking at an apple, the red color could have a higher weightage than compared to the actual size of the apple, probably, right? So there are certain input factors that might have a higher weightage compared to certain other factors. In this case, the W1s, W2s, and Wn's are associated with the input factors, and each input factor has a certain weight, implying how much importance it has in the final output. When you compute or when you actually multiply the inputs against the weights, you get what you call as a summation function. So that is what your cell body is actually doing, as we discussed in the previous slide. You're aggregating all of the information that came in from your five senses, you're putting them together, and then what you're doing is you're taking that from the summation, pushing it to a transfer or an activation function where the actual decision making happens. So when you've summed it up here, you've got a final value, and this is where your decision making is happening, where you're saying that, hey, this is an apple, probably a peach, or it could be possible that it's a lemon. I mean, I'm just giving an example, right? So it could be multiple classes. So that's how our brain processes information, and that's how an artificial neural network is also doing in this particular use case. So a simple example of the architecture of how a perceptron actually looks at. A couple of questions that have come in, but I'll just come back to the questions, Prabhakaran, Neetu, and Simran in a minute from now. I'll just explain some of the important aspects. But before I move on to the next slide, I quickly want to understand from the participants if there are any particular questions, if anybody has any questions in terms of the current slide. Okay, I'm guessing no questions at this point, but moving on to the next part. So if you notice it again, we've just made it a little more simpler in terms of the understanding of how the entire thing works. So again, the input data, you have a set of weights, multiply the weights against the input data and transfer that to, after you summed it up, you pass it on to the activation function, which is actually taking a decision. Now, it works well on a linearly separable data, which means it's easy on certain use cases when you want to, classify, let's say, sunflowers from a rose. Features are very, very unique for a sunflower compared to a rose. But, what about things that are non-linearly separable, which I will come back to at a later point in time. Now, these weights are the most important thing here because at the end of the day, the weights are the long-term methodology by which the algorithm is actually storing all of the information. So a lot of activation functions are actually in place. So to your question, Abhimanyu, in fact, is just moving to the activation function part of it. So before I move to that, but I just want to quickly talk about how the weights are actually determined, and that way, it'll be clear to understand the actual implementation of an AI algorithm. Now, weights are typically you would you can probably associate them with things like a coefficient. They're like a slope in a regression analysis. Initially, and remember, when you run a regression, you have only a single set of weights, but not in the case of a deep learning algorithm. You start off with an arbitrary value of weights, which could be probably as small as zero, but through iterations or multiple processes, the weights will actually improve. So what it does is it uses an arbitrary set of weights, multiplies the input against those weights, sums it up, passes it on to an activation function, and predicts an output. It already knows what the actual output is, so compares the predicted output against the actual output and finds out how different they are. The moment it knows there is a difference, what it does is it goes and updates the weight. And it keeps updating this weight until a point where the weight is able to predict exactly the output given the input. So the moment the accuracy is reached, it stops the updation of weight. So it might start with an arbitrary value like 0.01, but let's assume that 0.08 is the weight at which the input is helping the matching the output against the predicted output. So it takes 0.08 as the final output. So what it happens to do is across iterations keep updating the weights to identify the best combination of weights for predicting the output exactly. So as we can see over here, what we have is the formula is WJT plus 1, which is the new weight, is a function of the old weight plus n or eta, which means you want to decrease or increase the weight depending on the difference between the actual minus predicted into x, which is the input data set basically. Now, I know a couple of questions came in, which is basically what types of activation functions actually exist on the data. Now, there are multiple activation functions. What we're looking at over here is a step function. During our sessions or during our course, we go into the depth of what activation function is used at what kind of situations. In fact, this is a step function which is zero until a threshold is reached. The moment the threshold is passed, it starts to become a positive number or a one in this particular case. This is what we call as a binary or a step function. There are activation functions like the sigmoid activation function. Then there is this cosine function, multiple activation functions. All of these activation functions are available within TensorFlow to actually implement some of these cases. Now, depending on the end output or use case, you need to make an intelligent choice of activation function. I hope that answers your question, Abhimanyu. Now, there's another thing which Chetan has asked as how are weights decided? Weights are arbitrary initially, Chetan, but over iterations, the weights will change, which means, you might take a choice of an arbitrary weight, but that might not be the best choice. So you keep iterating until you reach the right weight. So that's how they are. They're not static, rather they're dynamic. Simran, is AI have any existences without deep learning? There are hard-coded use cases, Simran, which actually uses AI without deep learning, but they aren't scalable to the level at which AI deep learning is basically. Um, Yes, absolutely. Prabhakaran, is DL or ML, part of, is it important in speech recognition? Absolutely, it does help in that case also. Recognize speech context, rather. Sorry. So yes, it does in that case as well. And to your question, Neetu had asked a very interesting question, which is autoencoders. Why do we autoencode? Now, autoencode is basically, again, a family of deep learning algorithms that are unsupervised, which means unlike the data set where we have classes explicitly mentioned, in an autoencoder you do not have classes mentioned. So rather, it's a dynamic tool that can do a certain level of automatic classification or best known outputs that it has to replicate given the input. It can also be sometimes used as a dimension reductionality technique in this case, Neetu. Absolutely, Abhimanyu. So Abhimanyu's point here, so for a particular problem, only the weights are changed in every iteration and the activation function remains the same. The choice of activation function is something that we call on. It changes from layer to layer, but for a particular problem, it remains the same. So the activation function is basically how you'd like to get your output as, basically, right? A single layer perceptron for a classification. Now, as you can see, this is an OR gate. I think a lot of us have come across the concept of logic gates. Here, the output is called a true, which is basically one when both the cases or either of the cases are a one. The moment both the cases are a false, it indicates a false. So as you can notice over here, you have the x1 and x2, which is the input data. We've arbitrarily taken a choice of weight as one, basically, right? The input data multiplies with the output data, which means 0 into 1 plus 0 into 1, which is basically 0, and that gets marked over here in this origin over here. Similarly, 0 into 1 plus 1 into 1 is a 1, and that gets marked over here in x2. The same way x1 gets marked a 1, and then there is 1 into 1 plus 1 into 1, which is basically a 2, which get marked here. Now, t is equal to 0.5 is a threshold. Anything that crosses the threshold is basically classified as a separate group, and anything that's within the threshold is called as a separate group. Now, this is very easy for a single layer perceptron to classify. An OR gate is simply put when either of the cases are a true, or when either of the cases or both the cases are a true, the output is a true. Now, it is easy to do this because it's linearly possible, but the complication arises when you're talking about non-linearity in the data. And typically an XOR is when either of them are a true, it has to be classified as a true, but when both are false or both are true, it needs to be classified separately as a false. And as you can see, the same objective with which we built the earlier logic gate, you will notice that there is a certain level of misclassification that is happening here. Now, XOR is a kind of nonlinearity that exists in logic gates, and application of a single layer perceptron typically fails over here. And that is where you need to actually talk about multiple perceptron case, or what we are talking about here is basically the uh, more than two neurons kind of situation. A single neuron has the architecture that we just saw earlier. This architecture is what it has. And we are saying that we need to have multiple architectures like the same, which means multiply this by n number of times to scale up the algorithm. So that is what we're talking about when we get into a multi-layer perceptron and its application. In fact, as you can notice over here, you have the input data, x1, x2, x3, and then there is this y1, y2, y3. Each of these y1s have a summation function, as you can notice over here, and it also has an activation or a transformation function. The summation function, the formula as we talked about, is wi into xi. The transformation function applies a sigmoid transformation here, as you notice, which is 1 by 1 plus e to the power of negative bx. And what you have is basically, earlier you talked about a single layer perceptron. If a single layer perceptron is defined as x, you have a 3x over here, which is basically three neurons that are processing all of the information. One more thing that we didn't discuss about is basically the bias, and the bias is pretty much similar to the intercept that you come across in a linear regression. When all other input factors are zero, the bias is the value that the final output actually takes. But remember, bias has a larger function than that. It is very, very important to actually steer through the entire function. So whenever we look at the weights as your accelerators, you can call the bias as your steering wheel that is in control of your overall function and its application, basically. As I talked about it earlier, weights are basically that unit or that particular uh, component within a neuron that is very important to store information for the long-term perspective and be able to apply for new situations. And it is very important to update the weights, because in case the weights are a wrong choice, they are going to end up predicting wrong, and that is going to create a misclassification or failure of application. So we need to take a choice or a conscious, at least the algorithm has to take a conscious choice of weights to be able to predict the outcome as best as it can. In case it does not have the right choice of weights, it needs to go back and update these weights, and that is what we call as actually a back propagation, the ability to go back and update its learning. So simply put, if we know that an apple or the object that we looked at was not an apple, but rather it's a peach, what we do is we go back and update our weights, and we say that, hey, anything that is a little smaller than an apple and a little less red in color is probably a peach, and we can't call it an apple. So the same way, the algorithm knows that it has predicted something wrong, and it needs to go back and update its learning. So what happens is your input data actually comes in through the input layer, passes through a set of neurons. And if you notice here, this is almost 8 neurons, which is 8 times of our single layer perceptron. And all these 8 neurons are taking the input data, creating certain computations, and then passing it on to the next layer until you're finally able to receive the output. So that is where a multi-layer perceptron has got multiple computations, and the ability to scale it up from 8 neurons that you see in this case to probably 100, 200, or even 300 neurons is absolutely easy, especially in TensorFlow. And I will show that to you in a minute from now. But the most important thing is the ability to handle non-linearities in the data very, very efficiently. The training of a neural network is very important. In fact, the most common thing in neural networks is the concept of backpropagation. And in fact, I was just talking about that a moment before. So let's actually look at how it works in this particular case, right? So you have the input data, which is basically 0, 1, and 2, and your actual output is basically 0, 1, and 4. Now, you take a choice of weight. Arbitrarily, you take the weight 3, and you multiply it with the input data, basically, right? So 0 into 3 is basically 0, 1 into 3 is 3, and 3 into 2 is basically 6. Now, your actual output is 0, 2, and 4, and the predicted output using the weight is basically 0, 3, and 6. So we have a certain level of error. Now, the absolute error, which is actually the difference between the predicted and actual, as you notice over here, is actually 0, 1, and 2. But we square them off because there's a high possibility that some of the errors might actually be negative in this particular case, and adding up or summing up negative and positive values might result in a 0. So to handle that, we square them up and it becomes 0, 1, and 4. So that is where you notice that the square error is 0, 1, and 4. To handle this efficiently, we feel that okay, this is not the right choice of weight. So let us take another weight in this particular use case. So what we do is we add up a new weight, which is 4, and when we multiply that against the input, we get the outputs of 0, 4, and 8 this time. Again, this is way far away from the desired output of 0, 2, and 4. So let's actually look at what the squared error in this case is. It becomes 0, 4, and 16, which is really high, or 4 times higher than what it was for the weight of 3. Now the model knows that as it is increasing the weight, the error is increasing. So it consciously makes a decision. Rather, within the model is an optimization algorithm. During our sessions, we focus about or talk about the optimization algorithms in detail, and that is what we call as a stochastic gradient descent. And it identifies the right choice of weight. So the moment the stochastic gradient descent knows that the algorithm, when the weights are increasing, the error is increasing, what it does is it takes the reverse direction and starts to reduce the weight so that the error reduces to a point where beyond which you cannot reduce the error is where the optimized weight is identified by the stochastic gradient descent algorithm. As we can see here, you can notice that as you're increasing the weight, the error reduces initially, but after a point in time, you continue to increase the weight, you will notice that the error continues to increase. So it is called a gradient descent because regardless of where it begins, whether it's on the left side or on the right side, on top, it has to descend down to this point where the error is minimum or is absolutely low, basically, right? So that's how the training of a neural network actually works. Before I proceed to the use case, I quickly want to again take a pause. All the participants, I quickly want to check if there are any questions, if there are any clarifications that you guys would like to get before we actually proceed to the practical use case or application of neural networks on TensorFlow. All right, since there are no questions at this point in time, I'll talk about what is the practical use case that we're actually going to look at, or what is the multi-layer perceptron use case that we're talking about. Let's assume that you've been hired by a particular team to identify the difference between a mine and a rock. So the objective is to create a model that actually identifies a particular object as a mine or a rock. Now, this is an interesting use case because if you want to detect a particular object as a mine and a rock, there are a certain level of signals that are being sent out from the detection tool, which could probably be a sonar. And what you're going to do is use these signals to detect whether it's a mine or a rock. So what we're going to do is we are going to actually look at it in terms of, I'll first show you the data set. After that, we are going to read the data set into Python. We are going to define the features and labels. Then we're going to do something called as an encoding. I'll talk about what encoding is, and then we will divide the data into training and testing, uh, do all of the assignments and all of the storing of objects within TensorFlow, implement the model train, and then show you across iterations how we are basically reducing the mean squared error, or actually increasing the end prediction capability of the model, basically, right? Or in this use case, it's the accuracy that we are focused at. So let me quickly open the data set for you guys so that it becomes a little more clear in terms of how the data looks like. So I'll just pull that up. Give me a quick second. Sorry for that. This is what we call as the advantage of Python. So you love your Python so much that you process your data, all of it in Python and not in Excel. So yes, so you have 60 different classes, as you can see here. 60 different features. Sorry about that. All of these features are basically signals that actually come up from the Sonar tool. Now, each signal basically has certain value, and a combination of these features is what determines whether the final output is basically a rock or a mine. In this case, it's 0 and 1. And our objective is to find out, or through 208, as you can see, 208 instances, create a model that learns all the features that are necessary to classify a particular instance as a rock or a mine, and then apply it for future use cases. So intelligently, the moment a future use case comes, automatically the model should have the ability to predict whether a particular object is a rock or a mine. So let's see how we are going to do this in TensorFlow. In fact, I'm going to quickly open up my Spider, and this is a tool that is commonly used by all data scientists, especially when it comes to deep learning. Um, any questions at this point in time? Please feel free to use the questions panel. I'm more than happy to take a pause and answer them at any point in time. And we'll quickly execute this model, and we'll talk about the different aspects that are there within this model before we actually see the final output as well. So a couple of libraries that are very important. Matplotlib is for all the visualization of the data. We import TensorFlow because we would like to process all of this information in TensorFlow. NumPy is basically multidimensional array and a lot of processing in multidimensional array. TensorFlow, in fact, is a combination of NumPy and scikit-learn. It has the important APIs necessary to run deep learning algorithms, and at the same time also got the APIs to process a multidimensional array. So NumPy is imported as NP. Pandas is where our CSV file that we just looked at is going to be imported by and created as a data frame. It's easier to process the data frame, and it's easier to actually work with the data frame as well. So that is where we are actually bringing that in. Apart from that, from scikit-learn or sklearn, we are calling in three more packages rather. One is for label encoding, which I'll quickly show it to all of you guys. And then there is the shuffle. Remember, these 208 instances that you're seeing right in front of us are in a particular order. So if you notice the final output, let me quickly open that. You'll see that initially all the ones are there, and then there are the zeros. Now, although the model does not get affected by it, it is important that we actually shuffle the data set up so that we can eliminate any existence of bias that could probably be there in this data set. So that's why we're going to shuffle the data. And then after that, there is the model selection, which has the functionality of train, test, split. So automatically splitting your data. So splitting this 208 instances into training and testing. What you do by that is you train on a certain number of observations, and then you test it on the other observations to see how the accuracy works. So let's assume that I have 208 instances. I divide it into 100 and 100. Let's assume for our example right now. So on the 100 instances, the training happens. It learns all the features and then applies it on the testing data set. Now in the testing data set, I hide the rock and mine classification. Rather, I ask the model to derive that. And then what I do is I compute or I compare both the outputs to find out the accuracy basically. Right. So that is where it's important to divide your data into train, test, and split. Now, a quick function here to actually read the data set. In case you're not comfortable with Python, do not worry. We do have a Python session as well before the TensorFlow sessions actually begin. We have a prerequisite session that focuses only on Python and how to use Python or program using Python. So this function that we have written over here is to use pandas functionality to actually read the data set. And then what we are doing here in line number 15 and 16 is basically to divide the data into X and Y. Now remember, quickly opening up the data once again, remember that Y is basically the 60th column that you can see over here, which is what we have discussed in our example here, right? So Y is the 60th column. All the columns from 1 to 60 are basically what we call as the X, basically. Now, the rock or a mine or the class which it belongs to depends on all the 60 variables. That's why we separately call them as a X, and we call this as a Y separately, because Y, or the 60th column, is dependent on all the 60 columns before it, basically, right? So that is why we are calling them as X and Y, and we've used the functionalities within pandas to demarcate what are X and variables Y is, basically. So we demarcated the columns separately. We are applying an encoder, which is not necessary in this particular use case because our data is already in 0 and 1. But in case our data was not in 0 and 1, we need to encode it to make sure, let's say if it was rock and a mine, or if it was fraud, not fraud, we will have to use a particular example like 0 or 1 to recode them. So that is what we are doing here, not really useful in this particular use case, but we're just showing that it's a good thing to actually do. In a neural network, so Abhimanyu has a question here. In a neural network, what computation is taking place in multiple layers, and how does it affect the final output as composed to a computation which uses only a single layer? I'd like to bring the concept of big data here, basically. So what happens within Hadoop is basically you're distributing all of the tasks across different nodes or clusters, for example. The same way what you're doing in this particular example is you're distributing all of the work. So the neurons are freezed up. If simply put, if we had to have a single neuron in our brain to actually process all the information around us, there's going to be a definite traffic jam. So when we're using a multi-layer perceptron, what we are doing is we are distributing all of the tasks and making it easier for the algorithm to actually work efficiently and predict much more efficiently. So that is what we are actually doing in this particular case, Abhimanyu. So the processing time is faster and the accuracy is higher in terms of the final output. I hope that answers your question, Abhimanyu. Right. So moving on, encoder, as we discussed, is just a function to encode the variables, and there is also something called as one-hot encode. I just want to quickly call out what that basically means. Now, what a one-hot encode does is basically, let's assume you have the outputs as R and M. What a encoder will do is just convert this into 0 and basically convert this into a 1, basically, right? And a one-hot encode creates two new columns, and when there is a rock, it will basically call it as, let me put this down. So let's say it is 1 and 0. So when it is a rock, what it will do is it will, under the 1 column, it will put it a 0, and under the 0 column, it will put a 1. When it's a mine, sorry about that, apologies, 0 and 1. And when it is a case of mine, it will basically call it as a 1 and a 0. So this happens across columns. So this is what we call as a one-hot encode. And that has been defined in the next function that you see over here. So we've laid down a logic by which we can one-hot encode our data set. Simple functionality, but do not need to worry about it. TensorFlow within itself actually does provide the functionality or API for one-hot encode. So you don't need to write such a lengthy amount of code. Rather, it's just a function that you need to call out within TensorFlow to execute that particular thing. Remember, as I did when I missed out on this point, one hot encode, or for that matter, even TensorFlow is actually uh, it has the low-level APIs and the high-level APIs. So both of them are available. So which means if you want to prototype, it's very easy. At the same time, if you want to customize, it's highly possible with TensorFlow. So big advantages there in terms of TensorFlow. Next is using matplotlib. We are quickly going to plot a couple of things, which is basically plot the ones and zeros. Remember, our data is of ones and zeros, one indicating a rock and 0 indicating a mine. So we are just plotting that out using a matplotlib function, followed by a quick execution of all the functions that we've actually defined here. So you can see we've actually executed the read underscore dataset function, which will generate three datasets, or rather two important for us, which is X and Y. Then the plot underscore points, the same function that you see over here, has been executed here to execute the outputs of the dataset X and Y. Followed by a quick shuffle of data. As we've talked about earlier, it's important to shuffle the data because they are in a certain order, and the order might affect the biasness of the algorithm. So that is why we are shuffling the data and then breaking them into two parts on a macro level, which is train and test. As you can see, train X, test X, train Y, test Y, basically. So training data of X, which is the dependent variables available for training, testing data of X, which is dependent variables available for testing. Train Y is basically for training purposes. The test Y will not be fed to the algorithm, rather will be used for validation purposes by the algorithm to see how accurately it has been able to predict. Now, the size of breaking the data is 20% for testing and the remaining 80% for training. And for reproducibility of the results, we've kept the random state at 415. Couple of important things. Learning rate. I kept mentioning that the weights will increase and decrease, and the rate at which the weight should increase or decrease depends on the learning rate. So weights can increase by 0.3 or decrease by 0.3 across different iterations. Now, in this particular use case, I have given 3000 epochs or 3000 iterations rather. So which means there are 208 observations, and this model will typically go through all the 208 observations at least 3000 times, right? That's a big number, I agree. So it's going to do it for 3000 times, but just for the sake of time constraint for this point in time, I'm just going to keep it at 1000 so that we can see how the output looks like. I'm going to store the cost history. Cost is nothing but it is trying to find out what is the difference between the actual and predicted. So we are going to store that in an empty object so that we can keep looking at how it has worked out. Now, this is a multi-layer perceptron. The most important thing is I'm defining how many layers I have. Remember our earlier example? I'm sorry about that. Our example that we just saw over here. Now, in this particular case, you're typically looking at two layers with four neurons. I'm talking about four layers with 60 neurons. That is totally 200, 240 neurons, basically, right? Which is 240 times a single layer perceptron. Remember, a single layer perceptron can handle linear data, but non-linearity is not its strength. So this data has a lot of non-linearity, and that is the reason why we have four layers with 60 neurons each to process all of this data. We are defining the input data, which is X, already discussed as we've seen it earlier here, followed by the weights and biases. As I've discussed earlier, the weights are something that is kept as a variable, which is an object that TensorFlow actually provides, which means the values vary right from the start to the end. They've been kept as tf.zeros, indicating that initially the weights will start as 0, and as there are multiple iterations, the value will increase from 0 to 0 0.3, 0 0.6, 0 0.9, so on and so forth until it is able to arrive at the right weights. Same concept applies for bias, and then there is a y, which is basically the actual y that we're looking at. So that's basically the weights, biases, and then we come about the multi-layer perceptron. The first part of it that you see is basically the summation function, where you're multiplying the input against the weights and you're adding the biases. So you're adding tf.add and tf.matmul. So this is matrix data, so matrix multiplication between the input and the weights, and then the addition to the bias, which is basically the summation function. You take the value from the summation function and pass it to the activation function, which in our case is a sigmoid activation function. The same concept of the value is basically the input layer. The layer 1 becomes the input layer for layer 2, and the same concepts happen there also, which is the summation function and the activation function. These happen for four different layers, and remember, each layer has its own activation function. Here we are using a sigmoid activation function, and in the final layer we are using a ReLU activation function. During our sessions, we go into the depth of what these functions are, but considering we have a time constraint, we are not going into all the activation functions. But remember, the activation functions design your final output. They are the ones that are very important to actually help you decide the final output, basically. then followed by the output layer, which is where the outcomes are actually going to be created as. Now, although we've decided what our weights and biases are, it's important to discuss about the weights and biases for each hidden layer, and that's what we are specifying here through this particular part of the code, followed by the declaration of biases uh, uh, for all the hidden layers as well. So four hidden layers and one output layer for which we have actually specified the uh, biases as well. Now remember, what we've done till now is just compilation. So 0 to 118 line of code is all about the compilation. The actual execution happens only when we initialize all of these things. So that is where we are using the init function or global initializers to initialize all of the compilations that we've done, and to execute them is what this particular function does. The actual logic of the model is multilayer underscore perceptron. As you notice, the definition of multilayer underscore perceptron has been done here. And it takes all of the input data, multiplies it with the weights, and then adds up the biases. Couple of important things within TensorFlow to declare the cost function. And as I said it earlier, we are using a gradient descent optimizer to basically identify the best possible combination of weights to predict the outcome, basically, right? So that is what we have done in this particular use case. After having done that, this is a session. This code typically helps in executing all the things that we've just about listed. So all this while we were just writing codes. To execute it is this particular function, and we are just running a for loop against the entire data set to be able to show us how exactly the entire process is working. So we are providing the input data, the outputs, and the other things that needs to be validated for across different data instances. So 208 instances that need to run as an epoch, basically as an iteration over the epochs, and has to produce a multiple level of outputs. So I'm going to quickly execute this code, and there are a couple of plots that we have in the final part of the code, but I'm going to quickly execute this. And in the meanwhile, what I'm going to do is I'm going to pause it at this point in time so that, if there are any questions, I would like to take them up at this point in time. Please feel free to use the questions panel to type your questions. You can see that we started off with an epoch of, in this case, we started off with zeroth epoch, which had basically very low level of accuracy, but now it has been able to improve it to almost 69% in terms of the accuracy. Constant fluctuations, yes, there will be, in terms of constant accuracy is being measured at this point in time in terms of across epochs, how it is actually doing. So it is running across epochs. It is showing a couple of use cases where it has been able to get about 80% accuracy, and you can notice that as it is running through. Any questions, guys, at this point in time? Any clarifications that you guys would like to get before we actually proceed to, the final output? Any questions? We're almost down to the final epoch. Now, this is what I was mentioning that, this is a CPU. So considering the amount of processing units available within a CPU is very less, sometimes such kind of processing does take time. That is generally the reason why we prefer to execute some of these models on cloud. In fact, in EduReka during our sessions, we do have Cloud Lab set up within our sessions. So most of the times the students actually execute or the participants actually execute a lot of these codes on the cloud instance to be able to see, how this exactly works out. Definitely, Abhimanyu. I will actually ask the team at EduReka to send you the presentation. For those who are interested, definitely. Please do get in touch with also the team here. The support team will definitely get in touch with you after the session also. Now, feel free to let us know if you need anything else apart from the presentation as well. So if in case there's a requirement, I'll be more than happy to answer any clarifications that you have after the session also. But feel free to put your questions right away as well, because while I'm here, it's easier to answer a lot of the questions in this case. So almost about the last 15 or 20 epochs that are actually running. So if you notice, we've just about got to the end of it. So the final output is here. So you will notice that the final accuracy it has been able to arrive is at 78. But what is important is, yes, I've reduced the epochs from 3000 to 1000. If I'd allowed it to run for another 1000 or 2000, we would have been able to arrive at the level of accuracy. But notice the most important thing. We started off with an accuracy of 52%, as you can see in this particular object. But by the time we came to the 1000th epoch, we actually increased it to 78%. Now, across these epochs, the weights have changed, and it has the ability to change the weights to increase the accuracy from 50% all the way to 78%. If another few epochs I would have let it run, definitely we would have been able to arrive at a higher accuracy than what we are seeing at this point in time. But what is important is that applying the TensorFlow here, we have complete control of the algorithm, which means I have the control in terms of increasing the epochs or reducing the epochs, depending on the kind of problem that we currently have. So our sessions focus on tuning a lot of these hyperparameters. In fact, I know we've rushed through most of them because of the fact that we have a deficit of time. And during our sessions, our focus is in talking about what these different hyperparameters are, how they need to be tuned, and how they are actually supposed to be handled. What are the different aspects? In fact, we've looked at a 35,000 level right now, but during our sessions, we go down to the depth of each of these things to understand how this works. And also implement this on cloud because that definitely saves up a lot of time in terms of its accuracy. So it has shown across epochs how the accuracy has varied. Couple of epochs it has been able to touch almost 85%. So the model has not consolidated definitely, but just a use case to actually show how we are in control of the algorithm and different aspects of it. So I'm going to quickly pause here and will quickly take up if there are any questions that are there at this point in time. Not a problem, Shashank. Thanks for joining in. Definitely, I'll ask this team to actually get in touch with you at the email ID, and I will definitely ask them to work it out with you. But before anybody leaves, I just quickly want to I just need one quick favor from all of you, which is at the end of the session, there'll be a feedback form that will actually come up to you guys. I just request you to fill up the feedback form in terms of how we did this, so that it'll be helpful for us to understand how it went through. So definitely, to all the participants who want the recording or the things that we discussed during the session, the support team is there. They will be getting in touch with you and they will be walking you through different requirements. In case there are some other questions that you do have post the session or at a later point in time, feel free to shoot out an email to our team. They will definitely forward the email to me, and I'll be more than happy to answer all the questions because I know a lot of people are actually heading out as well. So that's the reason why, feel free to email me. But please do not forget to fill up the feedback forms that come up at the end of the session. Anybody who's leaving, not a problem. Thank you for joining us for the session. It was wonderful interacting with all of you. Those of you who are leaving, you're free to. Those of you who'd like to put down a couple of questions, I'm still available after the session. So feel free to use the questions panel and I'll be more than happy to answer those for you. Thank you so much.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!